This lecture will be over section 28.4. Here we'll be discussing a laser. So a laser requires a population inversion in which the population of atoms in higher energy states is enhanced. Through stimulated emission, many photons are radiated with the same frequency, phase, and polarization that are all synchronized. The laser is a light source that produces a beam of highly coherent and very nearly monochromatic light as a result of cooperative emission from many atoms. So the name laser is an acronym for light amplification by stimulated emission of radiation. We can understand the principle of laser operation on the basis of photons and atomic energy levels. So if an atom has an excited state with energy level E above the ground state, then the atom in the ground state can absorb a photon whose frequency F is given by Planck's equation. And you can see the process here, which shows that a gas in a transparent container, an atom A absorbs a photon, reaches an excited state labeled A star in the figure. Sometime later, the excited atom returns to the ground state by emitting a photon with the same frequency and energy as the one originally absorbed. This process is called spontaneous emission. So the direction of the emitted photon is random, and its vibrations are not synchronized with those of the incoming photon that started the process. In stimulated emission, in other words, what we're going to see here, an incident photon encounters an atom that's already in an excited state with the same energy above the ground state as the photon's energy. By a kind of resonance effect, the incoming photon causes the atom to emit another photon with the same frequency and direction as the incoming photon and with its vibrations synchronized with those of the incoming photon. So one photon goes in and two come out with their vibrations synchronized, and hence the term light amplification. Under proper conditions, a laser uses excitation and stimulation emission to produce a beam consisting of a large number of such synchronized photons. Such a beam of synchronized photons is said to be coherent. So you can see here in part B, you've got three interaction processes from an atom and electromagnetic waves. You can see the spontaneous emission, atom in its excited state, and you can see these things going everywhere. And you can see three interaction processes from an atom and electromagnetic waves. We've got stimulated emission, which again is different from the absorption, where it's picking it up, and the spontaneous emission, where it's just throwing the stuff wherever. The stimulated emission is basically throwing things out in the same direction. And again, you're seeing here, you've got light amplification going on where you've got one photon coming in and two going out. So suppose we have a large number of identical atoms in a gas or vapor in a container with transparent walls. You've got a moderate temperature, so if no radiation is incident on the container, most of the atoms are in the ground state and only few are in excited states. If there is a state with energy level E above the ground state, the ratio of the number of atoms in this state to the number of atoms in the ground state is going to be small. So suppose we send through the container a beam of radiation with frequency F corresponding to the energy difference E. Some of these atoms absorb photons of energy E and raise to the excited state. Population ratio increases. Because this is originally so much larger than this, an enormously intense beam of light would be required to increase this to the comparable value of N naught. But suppose we create a situation in which NE is substantially increased compared to its normal equilibrium value, that's considered population inversion. If NE can be increased enough, then the rate of energy radiation by stimulated emission can actually exceed the rate of absorption. The system then acts as a source of radiation with photon energy E. Furthermore, because the photons are the result of stimulated emission, They all have the same frequency, phase, polarization, and direction, and they're all synchronized. The resulting emitted radiation is therefore much more coherent than the light from ordinary sources in which the emissions of the individual atoms are not coordinated. This coherent emission is exactly what happens in a laser. So it can operate over a broad range of the electromagnetic spectrum from microwaves to X-rays, and in recent years, lasers have been found to have a wide variety of practical applications. The high intensity of a laser beam makes it a convenient drill. So in other words, you can make a laser beam, drill a very small hole in a diamond for use as a die in making very small diameter wire. Because the photons in a laser beam are strongly correlated in their directions, the light output from the laser can be focused in a very narrow beam, and it can travel long distances without appreciable spreading. Surveyors can use lasers, especially in situations in which great precision is required, such as a long tunnel that's drilled from both ends. And lasers can be used in medicine, where you can basically vaporize anything on its path. The properties used to treatment of a detached retina. A short burst of radiation damages a small area of the retina, and the resulting scar tissue welds the retina back to the choroid from which it had been detached. Laser beams have surgical applications. Blood vessels cut by the beams tend to seal themselves off, making it easier to control bleeding, and it can also be used in the removal of tumors.